Hello, welcome everyone. How was the breakfast? Was it good? Did you have a good breakfast? That's good because I'm going to take you on a long journey, a long, stressful journey on the bumpy road to universal JavaScript. So, I'm Johannes. Hello. You can find me on GitHub with that handle. And on Twitter, it's one and more because I always add ends until the account is free. So that's a good strategy. And I also founded a company called Perigon with my friends. And I'm also a member of the webpack core team. So before we start the journey, let's do some journey preparations. So what's universal JavaScript? Do you remember that slide from yesterday, from Hassan's talk? Sorry about the shitty photo. My lens is kind of blurry. But what if you could have both of it, like the better first meaningful paint and the consistent SEO performance of server-side routing, and faster routing after the initial load and smooth transitions and changes of client-side routing? And that's exactly the idea of universal JavaScript. So the term is used to describe a special type of web application. It means that the application code is written in a way that it can be executed both on the client and on the server. So how does it work? The server renders the initial HTML and sends it to the browser. Then the browser displays the initial HTML, and simultaneously, it also downloads the single-page app in the background. Once the client-side code is ready, the client takes over and the website becomes a single-page app. And this process is called hydration or rehydration. But why would we want to do that? So the reason number one is performance. Because with server-side rendering, the first meaningful paint happens sooner. And that's because we're leveraging one of HTML's strengths, progressive rendering. Because the browser is incredibly good at rendering partial content. And that comes from the time where we had dial-up connections. So we could already start to read the text and didn't have to wait for the images. And that's a really good feature of browsers. But with single-page apps, we throw all of these built-in performance optimizations away. And that's not good. Reason number two is SEO, of course. So search engine crawlers used to not execute scripts. Nowadays, they execute initial scripts. But they usually stop after a while, and it's about 10 seconds, but you never know. It's a kind of a heuristic there. And another problem of single-page apps is that you can't set meaningful HTTP status codes. Usually, you just send a status code to 100, and you're good. And the reason number three is error resilience. Because the website stays usable even if scripts weren't loaded, blocked, or failed in some other way. And they can fail in a lot of ways, because we don't know the device where the website is going to be executed. So there are a lot of pitfalls, and I think you all know that. So when I prepared the talk, I want to go back to the roots of server-side JavaScript, and it turns out that the history is pretty long. Because JavaScript was actually designed to be executed on the server as well. Back in 1995, Netscape released this server-side JavaScript implementation, which they called Livewire. And the implementation looked like this. So you had this HTML document, and then you could have these server tags, and then write some output, and then close the server tag again. And it kind of reminds me of the programming model of PHP. But that idea didn't really take off. And so I came across a particular review from 1998. It's really good. So the developer says, I spent 18 months during Livewire development, and it's pretty lame. I hit the wall of scripting languages limitations quickly, and even though Livewire in Enterprise Server 3 added a lot of stuff, it still sucks. For this reason, I have dedicated a whole page on my personal site to describing why live fire sucks. And the page is still online. Yeah, random developer rant 1998. But I think he's right, because universal JavaScript can be very challenging. And that's why I want to show you some of the pitfalls that you can avoid them. So let's start the journey. And the idea is that we start from a single-page app, because that I think you're most familiar with the architecture. And then we progressively turn that into a universal JavaScript. And the full journey of this change is on this repository. So if anything is not clear, or if you don't understand it, then go to the repository and read the README. And of course, there are also multiple solutions to the problems. So that's not the only one solution, as always. It's just my own opinion. And as a last note, if you want to measure performance with that example application, you won't really get good numbers, because it's a quite small application, and you need a bigger application with bigger bundlers to see the effect. So how does our current single-page app look like? Where is my cursor? Ta-da! So our single-page app is a page that displays random Fox images. And it turns out there is of course, there's a web service that provides you with random Fox images. So I just hit the refresh button several times, and the image loads, and it's really nice. And that's our single-page app. The tech stack is webpack, BABEL, and React. But that doesn't really matter. It's more about the concept. So you can apply the learnings to different tech stacks as well. So let's start. This is our server.js. It's a regular Express server. We add this get handler that forwards any incoming request from API Fox to the remote Fox API that provides us with a random Fox image. And that's because we can't just do a cross-origin request. And then what's really typical for a single-page app, you have this this star handler that catches every request and sends the index HTML, which kicks off the single-page application. Our app.js looks like that. So we have this component will mount hook, which is called as soon as the component is added to the DOM. That's where we fetch the image from our own API, which proxies to the remote API. And then when the image is loaded, we set the state. Here's the Fox image. And inside the render function, we have the switch. We check, is the Fox image ready yet? If no, we display this loading indicator. If the Fox image is ready, we display the image. And our start.js looks like that. We import the app, call React DOM render, pass the node, and we're good. So the challenge number one is the Node browser gap. Because Node.js uses a different module system as browsers do. In Node.js, we have common.js, and we also have core modules like the FS module or the HTTP module. And on the browser, we have ECMAScript modules, and we have no core modules. So the good news is both platforms are getting more and more similar. So for instance, if you take a look at this example code, this could be perfectly valid on both platforms. So, and soon, this will be executable on both platforms, because, for instance, the URL constructor is going to be added to Node.js. But the bad news is we're not there yet. And in fact, our app component here is neither executable in the browser nor in Node. For instance, if you take a look at the import statements, we have this bare import specifier, which is the React string. We call it bare import specifier, and that's the thing that comes from, if you want to load something from Node modules. And we also import an image, which is not really spec'd. It's a kind of a webpack feature we're using there. And we're also using this custom syntax, JSX, but if you're using Vue.js, for instance, and using Vue components, you also have this custom syntax that's not really supported by the browser. And we do that because they allow us to develop faster. So the solution is use a bundler to streamline the module system and platform environment. And we create a bundle for both the browser and for Node. So how does it work? So in our webpack config, for instance, we can export 2 configs in an array. And this switches webpack into the multi-compiler mode. Our web config has this target web, which is implicit anyway, but I've added it explicitly here. And the Node config has this target node. This tells webpack the output should be prepared for Node.js. And we also set the library target to CommonJS2, which creates a CommonJS module that exports a specific value. And as a slight performance improvement, we can also configure the externals option, which tells webpack, don't take a look at the Node modules. They are fine. You don't have to transpile them. And this usually speeds up the compilation a lot. Another way is also to use or write isomorphic modules. And isomorphic modules are modules that expose the same public API, but that have different implementations under the hood. So for example, isomorphic fetch. They have, in the package JSON, they have 2 fields, the browser and the main field. The main field is for Node.js, and the browser field is respected by most bundlers and can be used to load different code that's intended for the browser. So the next challenge is the client-server gap. Because on the client, we have just 1 user, and on the server, we have multiple users. And there's also another difference. In the client, the result of our app render is a DOM update, and the result of our server render is an HTML document or HTML string. So how can we merge these 2 environments? So the solution is we keep the process stateless and maintain the application state for each request. In general, we design the app in a way that it can be used by multiple users at the same time. We also create 2 app entries, 1 client entry and a server entry, and that's the place where we can put all the platform-specific stuff. So in our example, we split up the start.js into a start server.js and start client.js. And on the server, we use this different rendering method that, for instance, when you're using React, this is this React DOM/server, which renders it to a string. But other frameworks have different renderers, and it should be possible to apply it there as well. And then our index HTML looks like this. We require the bundle, the server bundle that we just created. If you take a look here, I require from the dist folder. And then we insert the generated HTML at the place where we want to have it in the index HTML document. And on the client, start client.js, we have this, we can use the hydrate method from React to synchronize the application, the component tree with the generated HTML that comes from the server. The next challenge is data fetching, because we need to design the data fetching in a way that it's executable on both the client and the server. Why? That's because the initial requests will always be handled on the server side, and subsequent requests, which I call navigation events, will be handled on the client side. And you always need to remember that the initial route is not always slash. It can be any URL. How do you do that? So for instance, you could use Node Fetch, and this makes the Fetch API available in Node. And you also need to remember that on the client side, you can't do cross-origin requests. So every time you want to request something from a remote API, you need to proxy it via your own API to make it accessible for the client. And you should also use absolute URLs to fetch data from your own API. Why is that? Yes, your server may end up doing an HTTP request against itself, which is kind of weird, but it's fine, really, because it gives you the possibility to separate these two applications, like your data API and your server render app, and host them on different infrastructures. And if you're using GraphQL, for instance, you can also circumvent that overhead by using schema link, for instance. But there's also another problem, because when I go to the website now, I get this HTML back from the server. And you can clearly see it's the loading state, not the final state of the application. And that's because we are fetching the data on component did mount. But rendering, at least in React, is synchronous, at least for now. And this means that the server sends out the HTML in the loading state, not in the final state. The solution to this, you could do multiple render passes. So you call render again and again until all component did mount hooks have been executed. That feels kind of hacky. And it's also hard to define like a maximum number of rendering passes. So the better solution is to separate the data fetching from the rendering. So instead of having this component will mount hook, you create a static function that can be called before the rendering is happening. So instead of calling setState here, we return the data. And this is pretty similar to what Next.js is doing. They call it getInitialProps. Then on the server, in the start server.js, we call the static function app_fetch_data and then render the app. And now we get the final application state, which brings us to the next challenge, to the state dehydration and rehydration. Because when we open the console now, we see that React is providing us a warning. And that's because we are rendering the app with different props. On the server, we have the initial props that we just loaded from the remote API. But on the client, we call hydrate with no props at all. And that's where the mismatch comes from. So we somehow need to make the props from the server available to the client. And we can do that by, instead of just returning a string from the start server.js, we return an object with the string and the state that has been used to render the app. And then in our index HTML.js, we can use JSON stringify to stringify the state and attach the object to the window object. But now our cross-site scripting alarm just went off. Because you need to remember that the application state may contain user data. And if the user happens to decide to have a name, for instance, with a script tag, you may end up with an HTML document that looks like this. Because the browser just looks for an end of the script tag, and as soon as there is a script tag closed, the browser assumes, oh, that's JavaScript, it's invalid, so there's a syntax error, let's execute the other stuff. And then you have the cross-site scripting problem, and the browser happily executes the alert. And you can avoid that by replacing all the opening brackets with their Unicode counterparts. And this prevents this kind of attack. Then on the client, you call hydrate, and you use the state that you just attached to the window to rehydrate the application with the same props. Which brings us to the next challenge, the uncanny valley. So what's the uncanny valley? Back in the 1970s, robot engineers realized an interesting phenomenon. So back at the time, they tried to build robots that look more and more like real humans. And at first, people are really excited. Wow, this robot looks like a real human. But the more they came close to resemble a human face, they realized that people got freaked out. So there's this, the more it gets similar, and then suddenly there comes this uncanny valley where people are really scared. And it's exactly the feeling you get from this face. It's kind of awkward. And the interesting thing is, the phenomenon can also be observed in user interfaces. So it's when the interface looks really familiar, and you want to click a button, but the button doesn't respond. And in particular, in server-rendered apps, it's when the website looks usable, but does not respond to any user interactions. And Paul Lewis created a good infographic which describes the problem. So when the HTML arrives and the view is painted, you don't have the JavaScript for the interaction yet. And when the JavaScript arrives and is parsed and evaled, then you have the interaction. But between that, that's the uncanny valley. And the bigger your JS response size is, and especially the parse size, like the browser needs to parse and evaluate the big chunk of JavaScript. And the bigger that is, the bigger the uncanny valley is. So what's the solution to this problem? Of course, removing or replacing unnecessarily big dependencies is always a good place to start. Think about your dependencies, what you're including into the initial JavaScript. And Sean is really passionate about that. You should use code splitting to reduce the initial payload. So you can delay dependencies that are not immediately required with the import function. And as a last solution, you should use anchor tags instead of click handlers, because anchor tags are usable as soon as the HTML is rendered. Click handlers are not. They depend on JavaScript. So the general goal is, while the scripts are being loaded and parsed, our web application should already be usable. And this means that every meaningful UI state should have a URL. So take this example with a modal. So you get to example.com, and then you get these intermediate states, which are like spinners, content is loading, and then suddenly you reach this final state where nothing happens until the user clicks something. And then the user clicks on an anchor tag, and you go to the next URL. For instance, you can model it with a query parameter, show modal, and then you get to the next state, and then the user clicks on the back button, and you get to the initial state again. And this approach allows the server to fill in for the client when it's not ready yet. And there are also other advantages. The back button just works. And open a new tab just works. This is great. And I think it also results in better accessibility in general. And I think the easiest approach is if you use a library, a small library like the nano href, which captures all the anchor tags in the document and allows you to invoke a callback like this. And then you can react on the client side to the change. And that's how you can avoid to do a full page refresh as soon as the client is ready. So there's this next challenge, response streaming. When you take a look at our network graph, it currently looks like this. So we go to our website, and then we spend a long time just doing nothing, just waiting for the initial HTML to arrive. And the browser just sits and can't do anything because there's no HTML yet. But if you take a look at the second row, you see that the client JavaScript, we could already send that to the client because it's static. It doesn't depend on any user data. We could just send it. And I think the easiest solution right now is we need to write the server entry in a way that we can send out parts of the document as soon as they are final. So if we change our start server.js into an object that, for instance, exports the status code with a promise, then the document title, the HTML, and the state, we can send out chunks in the index HTML as soon as they are ready. So here we call start app. We get this object back. And then, of course, we need to await the status code because we need to set the status code before sending any of the HTML. But then we can use this, for instance, this nice module. It's called stream template, which is a tag template string, if you haven't seen that syntax. It's not in syntax error. It looks like that, at least to me, but it's fine. And it takes this template string and returns a Node.js stream. So we can pipe that to the response. And it takes all the promises and waits until they are resolved and sends out the chunks as soon as they are ready. And this changes the network graph into something like this. So while the HTML is, while the data is loaded, while the HTML is being rendered, we already sent some HTML to the browser, and the browser can start to request our JavaScript bundle, for instance, or other static parts of the document. So further challenges with if you're using long-term caching, if you're using these hashes in the URL, you can use the webpack assets manifest, which generates a manifest JSON, and this maps the source names to the dist file names. You also need to consider other request methods like post, put, patch, and delete. And you can use the form tag to use that. And you always need to remember that from a form tag, you can only send get and post. So if you want to emulate put, patch, and delete, there's this nice express middleware method override that allows you to define like the real method you want to use. And then it's the same approach like with the anchor tags. With the form, you wait for submit events on the document, and you just handle them on the client side. So when the client is not ready yet, we send a real request to the server. When the client is ready, we just catch the submit event and respond on the client to that event. And of course, the router needs to take care of these. And since your server is accepting post, put, and delete, you also need to think about CSRF protection. But of course, you can also decide to design your app in a way that it only accepts GET requests on the server side. Because, yeah, I think it's a design decision. You also need to take care of 300, 400, and 500 status codes, both on the server and the client. You need to think about the authentication, because usually with an authentication, you do a request against your own API, and then the API returns a cookie, but now the cookie is on the server, because on the initial renderer, we are on the server. So you need to make sure that the cookie is forwarded to the client. And of course, you need to make sure that cookies are not shared between different users. So there's kind of an potential problem here. If you want to get into the details, you should take a look at these frameworks. There's RESL. It's framework agnostic, so you can use it with React, Vue, Angular. There's Next.js, of course, which is the most popular one for React. There's After.js, which is kind of like Next.js, but with React Router. Then there's Nuxt.js for Vue. And if you enjoy reading scientific papers, you can also read my master thesis. It's also about the topic. Thank you.